stuff the bag, or not gave it to you, but made you go pick it up. Let me say it that way, because that's actually what happened. I loved that you guys started playing with that. You just started playing. Some of you guys made neat three-dimensional figures, and some of those I'm going to reference as today. So some of you guys made prisms, some of you guys, and I try to point it out to you. Oh yeah, that's called this, that's called that. So it's really cool when you're going to do manipulatives to just give it out to students and manufacture something so they have time to just play with this stuff before you've done anything. Because very often, somebody's going to do something that actually relates to what you're going to do with them, yes? Or that just let them play with this stuff just to get used to it. Okay. So, what we're getting into are these three-dimensional shapes. So how do I construct these shapes? So if I take these parts, and we'll play with these next time if you bring your stuff. All right, let me see. Now, these are kind of trippy, but they are trying to be rectangles. Would you agree? They just are trippy so they can connect better with each other, yes? So if I connect these two things, if I can, oh, here, sure. So if I connect these two things, which you guys want to go ahead? Do you see how if I tilt it, if I rotate it, it might connect better with another piece? Yes? As I do that, am I not changing the angle at which these, you guys all with me? So if I want to use two more pieces, I might do this. If I want to try to use one more piece, I might try to close it off a little bit more. All right. This angle that these two make with each other, so if I look at it straight on, it looks more like just two rays, yes? Two line segments. And then the idea of an angle makes a little more sense. Because the idea of an angle with these two planes is a little bit weird. Are you guys all with me? So if I think of a line segment that kind of lines right up with another line segment here, the angle between these two planes would be the angle between those two line segments. So if I just do this, it looks more like two lines. We call that angle, oh, this is kind of nice. We call this angle a dihedral angle. Of course we do. Why couldn't we call it something less weird? So dihedral angle is just the angle I create when I put two planes together. I wish I could turn this one light off. I'm going to dim the lights just a bit, if I can. I keep forgetting to ask somebody to come here and take a look at this. I should be able to shut that light off, but I cannot. It irks me. Okay. I'm almost certain none of us have ever heard the word dihedral before. It sounds like a chemical, almost, like a chemistry thing. And it actually sort of is. Now, when I connect these two things, if I were to connect two more of them and then put a top and a bottom on them, these each would be a face of the resulting shape. So if I take this guy, of course, it's got a little hole in it, but that's okay. I think my colleague was using it as a flask, maybe? I don't know. If I connect things together, what do you call this? A face. So that would be a face. So this particular shape is made of rectangles and what looks like it's probably a square, yes? So each face is a polyhedron, polygon. And then if I connect a bunch of polygons, I make a polyhedron. Okay. This is the face. This we call an edge. And this, what do you think I call this? Same old thing we called it before. Vertex. I love it. And just to show you a potentially better representation of that, here. Yeah. So that's the face, that's an edge, and that's the vertex. If you take any two sides in that shape, how do they meet? They of course meet at one edge. Yes? Okay. Like it. Oh, I'm sorry. Did you get that? Sorry. Okay. So faces are the polygons themselves that we're using to put this thing together. And one little extra side note here. I don't know. You guys at home, I don't know. Let me see. Yeah, okay. What is true about these two line segments along the top? Can anyone tell me anything true about those two line segments? What relationship do they have with each other? Parallel. Kick-ass. What about these two line segments here? Sure, but what do they do with each other? Intersect. In fact, in this specific polyhedron, they make a 90-degree angle, of course, because this is a square. It's crazy. Good job, Jim. What about, all right, do you all agree this line and this line are parallel? Yes? This line and this line are parallel. What about this line? Let me see if anybody remembers. I've talked about this before. This line and this line. Yes? This line here, yes? This line here and this line down here. Do they ever meet? If I extended this line forever and this line forever, would they meet? But are they parallel? Does anyone remember? We've talked about this before. In order to be parallel, the distance between the two of them must remain a constant forever. This line, if I send it off forever, and this line, if I send it off forever, they never meet. But does the distance between the two stay the same forever? Hell no. So here, let me give us something in the room that might be better. This line, that's the edge of the meeting of this polygon, this rectangle, and that polygon. They meet at this edge, correct? And that would be a line if I let it go forever, correct? And then that line, the corner, just down here, yes? They never meet, do they? You guys with me? I'm sorry. Some of you guys want me to continue. Okay. So that line there, and that line down here, yes? They never meet. If I go right here, how far apart are they? They're this far apart, yes? But if I let them go, do they stay the same distance apart? No, this distance keeps getting bigger. I'm getting further away from that line, yes? Okay, so those, who remembers what those are called? Anybody? Perpendicular would mean they meet at a 90-degree angle. I'm talking about two lines that are not parallel, but they don't meet. These are called skew lines. Okay. So just because we're talking about the elements of a polyhedron, some of the edges might be parallel, some might intersect, and some are going to be skewed to each other. Skew lines can only occur in more than 2 dimensions. So for the purposes of this class, we'll say skew lines can only occur in 3 dimensions. Not parallel, don't intersect. That's skew lines. They don't intersect, but they're not parallel. Do you guys see how that could only happen in 3 dimensions? S-K-E-W. You guys with me? So if I ask you to draw on your paper 2 lines that do not meet, they have to be what kind of lines? No, if I ask you to draw on your paper 2 lines that don't meet, can you do that? Draw 2 lines that do not meet. So draw a line, draw another line that does not meet that line, ever. What do they have to be? Good, because how many dimensions am I working with on the paper? 2. So in 2 dimensions, do you understand why I'm spending a little extra time? Because skew lines are weird. We live in 3D. We don't work mathematically with 3D very often. So if I just said, what do you call 2 lines that don't meet? People would say parallel. And do you see now how that is wrong? That is, if it's 2D, if 2 lines don't meet in 2 dimensions, they have to be parallel. They got nowhere else they can go. But in 3D, there you go. That's all I got to do. If you give me the option to go this way, I can go, oh, shit, look at that. Not parallel. They don't intersect. Yes? Okay, I'll stop. When you start teaching students about this, they're going to be just as kind of freaked out because they're so used to, of course, why? Because everything they've done has been on a piece of paper. And a piece of paper, unless you're a really good artist, is automatically 2D. Okay, I like it. And you guys might be able to tell that I am not a very good artist. So let's get into the topic at hand. Polyhedra. You guys know poly, correct? You guys remember, just to bring up traumatic experiences, algebra, polynomials? You remember polynomials? Do you remember binomials, trinomials? Some of you guys are like, I'm going to say no, and you can't make it. Does anyone remember what polynomial, like binomial, trinomial, what do those mean? 2 terms, 3 terms. Polynomial just meant many terms, yes? Polyhedra, this is kind of cool. Do you guys, okay. Do you guys all agree that this guy has a lot of seats? What do I mean by that? I can sit him down like that, yes? I can sit him down like that. I can sit him down like that. I can sit him down like that. Yes? So doesn't this guy have many seats? Would it make sense? If I just said this has many seats, you'd be like, what the hell's wrong with you? But now that I've done a demonstration, this has many seats, yes? You guys, and you can imagine like a 20-sided die that has many, many, many seats. And you roll it, it'll eventually pick a seat to sit on, and you're hoping it's like a nat 20 or something. Okay. You guys still with me? So that's exactly what the shit that means. Poly means many. Hedra, it's a part of the word. It means seats. That's many seats. That's kind of silly. Okay, I like it. Guess what this is officially defined as? If I take a bunch of polygonal regions. Oh shit. So this is the union of many, that's the word many, polygonal regions. Let me be more specific, because there's more to this. So when I put together a bunch of triangles, and some of you guys did this when we first started playing with our kits, put together a few triangles, you can make this little enclosed region, yes? So that's a part of this definition. Enclosing a space, a region in space, without any holes. So this poor guy has an issue, but he'll be okay. Where any 2 faces meet along an edge. I want to say at most at one edge because, for example, this face and this face never meet, right? So any two faces that do meet, they meet along an edge. So, is a sphere an example of a polyhedra? Why not? Because it's... Okay, doesn't have any edges. What was a polygon again? What had to be true about a polygon? Let's take a go way back to, so I have a simple curve, I have a simple closed curve. A polygon added one extra thing on top of a simple closed curve. It had to be composed of line segments. So the minute I've got this three-dimensional shape made out of polygons, it can't have any curved edges because it's got to be composed of line segments, which is basically what an edge is. So that's why that worked. Okay. Oh, let me see. Do I have any? Yeah. Yeah. Let me see. I'll try to show you this here. Some other weird stuff on this paper, but this. What do you think is? What do you think I'd call this? It looks like a piece of cheese. Does it? Do you see anything? This is a polyhedron, yes? But it's got something different from this guy, and it's an idea, two words, both start with C. Yeah, good. So what would this one be on the paper? Concave, because it caves in on itself. And of course this would be convex, because it doesn't cave in on itself. You guys with me? Can I pick two elements that live inside the volume of this thing, and when I try to connect them, I have to leave the shape? Still the same definition. Okay. So if you were kind of happy that we left concave and convex behind, we didn't. I'm sorry. But I think most of us are cool with that. Okay. So I already pointed out the faces, the edges, the vertices. That's going to come back in a big way in a minute. So we got faces, edges, and vertices. Oh my. Okay. So before we come back to that, we're going to do something very mathy with that in a bit. I want to talk about another shape that some of you guys created. This is a special, now of course, this doesn't have a hole, it's actually filled in, which is good. What would you guys call this? Cylinder, yes? What's special about this compared to like, well that would work too, but what would you guys call this? Sorry, for those of you at home, cylinder, this. What would you call this? Pyramid, yeah, I would call that a pyramid. Yes? We'll talk about pyramids here in a bit. What is different about these two besides, now obviously, is this a polyhedron? This is not. But the reason I picked it out of there is I think it's the only, well, do I have the, well actually that would work too, Jeff. You can do it, buddy. Here. This polyhedron, yes? What's different about this is, isn't it kind of consistent throughout? If I cut down this side and looked, let's pretend like this was solid, yes? So it was a good year, and for Easter you got a solid bunny, not the hollow bunny where you're like, oh, mom and dad aren't making much money. You guys gonna, do you guys live that? Okay. If I chopped down the center of this, if it was solid, and I looked at the face, would it look the same as this does? All the way through, correct? So any shape that is three-dimensional and it has this a repeated shape. So one seed of it is a certain shape, and that's repeated along the whole thing. If I slice it somewhere, it's the same shape. That is called a prism. So this is a very, very basic prism. So have you guys ever drawn Cubes, for example, right? Have you ever been bored, like right now, and you drew a little cube or something, you're just doodling? Anybody? Couldn't you do the same thing with a triangle? Make a Toblerone, yes? If I slice this down the middle, isn't it going to be a triangular shape? That is a prism. So any three-dimensional shape where if you slice it somewhere it's the same shape as the ends, a repeated triangle, a repeated square, a repeated circle, that's what a cylinder is. That is called a prism. Now, of course, when I say prism, what do you guys think about? Normally what people think about is a certain kind of thing. Prism? If I say prism, do you guys think, well, that's just somebody with a speech impediment that tries to say prism? No. When I say prism, does anybody think anything related to light? What do you think about when I say prism related to light?
Something that goes through it and then it has a rainbow.
Yeah, you've seen those images. You have the light coming in, and then it gets broken out to its different wavelengths, because different wavelengths of light get bent through another medium differently, which is neat. There's a whole lot of physics I'm not offended in, but you've all seen that before. You have a little lens, if you put it a certain way, you get a little rainbow because of the prism effect. So a lot of times when I say prism, people go to that rainbow image, but in mathematics, a prism has a very specific definition. Okay. So how many kind of prisms are there? If all a prism is a repeated shape, how many kind of prisms are there? There's basically an infinite number of them, yes? How many sided figure could you have something like a computer create? Could a computer create a 100-sided figure? Can you guys imagine a 100-sided, each side is like beep, 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 yes? You guys kind of with me? 100 seats, yes? 100-sided die, I roll it, beep, 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 yes? So if I just repeat that shape, that's another prism. So it's basically an infinite number of prisms. All right, I'm not going to continue going on with prism. I think you guys get the idea. So a prism, repeated shape, along a length. Two opposite faces are identical. Now, in this book, they claim a prism specifically must be created from polygons. They are not correct, but that's okay. What I'll say they're doing is, for the purposes of the book, they're going to say a prism, for the purpose of the book, are identical polygons. But we know that prism is a broader idea. You guys all with me? So when the book says prism, they mean specifically the ones you can create from a polygon. So a cylinder, for them, they wouldn't consider it to be a prism. Okay, I like it, I like it. If you have a prism, and so real quick, some of you guys made prisms. Do you guys remember when you were playing with the faces? I knew that at least one group made a prism, and I pointed it out to you at the time. And you're all like, I don't even remember you, man. But what was interesting was, if I have some shape and I try to make a prism out of it with pieces, do you see I have to make this, what's true about the sides that connect each piece? If you look at the picture, what's true, what must be true? So if I took, Jeff, hold on, let me grab, see if I still have one, yeah. So what is this trying to be? It's a little bit wonky, of course, because it's got the edges so it can connect. 1, 2, 3, 4, 5, 6, yes? So if I connect another hexagon to this, what must I connect it with? What shape? Yes! A rectangle, a square, even a parallelogram, because I could have a tilted. So if I have something like this, I'm going to make a cylinder just because it's easier for me to draw. Yes? that is a tilted cylinder. Some call it shifted, tilted, whatever, slant cylinder. That is still a prism because every cross section would still be a circle, yes? Okay. Now, real quick, circles are not what we're considering. So if we consider prisms to be, I love you guys, I love you guys. There's nothing too crazy. If we consider prisms to be polygons that are connected to each other, doesn't each edge of whatever polygon I use, doesn't it have to connect to a rectangle like we just said, right? Those rectangles or parallelograms in general are called the lateral sides. That's crazy. Well, actually, even better than that, lateral faces, because lateral means side. And if I create a prism from a polygon, those lateral faces must be parallelograms. If my prism is made from polygons. I want to give every Y an extra loop. Okay. Oh man, I have made a mess up here. Okay. Yep. If those lateral faces are rectangles, this is not going to be very surprising. We call this a right prism. Just like a right triangle has a right angle in it. If I use rectangles, they have right angles. We call it a right prism. Does that make sense? If it's tilted, there's no way it must have parallelogram edges. We would call that an obtuse prism. So if it's not a right, meaning it's got parallelograms, then it would be an obtuse prism. Okay, I like it. Let's focus on pyramids a little bit. Let me see if I can get you guys to try something out for me. Can everybody make like a parallelogram on your paper? Can you pick a point kind of hovering over, more in the center, like pick a point kind of hovering over that, sort of in the center. It doesn't have to be perfect center, but pick a point hovering over your parallelogram. Take every corner, every vertex of your parallelogram and connect it to that point. What have you just made? Pyramid, cool. So if I put a triangle down here and I picked a point and I connected, I get a pyramid, yes? Cool, I like it. So it's basically this guy. Now these, of course, are vertices. This one's special. That's the one that everybody kind of comes to, yes? Does anyone have any clue what I might call this guy? It's the upper, it's the top of this thing. I think of this as the food chain. This is the one at the top. Apex, I love it. So this point here is called the apex. Now, so this book, I do disagree with it in a few places. What do we call a shape if the base I choose is a circle? And I do the exact same thing. This is where things get a little weird. If the base is a circle and I pick a point above it, and then I say every vertex connected to the point, What's your first immediate objection to my instructions? The circle. Does it have any vertices? No. Okay. I love you so much. This is so cool though. You ready? Every time we increase the number of edges something has, a regular polygon, so if I have a regular hexagon and then a regular octagon, and I just keep increasing the number of sides, doesn't it become more and more circular? You guys with me? So if I had a 100-sided figure and I looked at it from very far away, would it look like a circle? Can you imagine that? Okay. So a circle has an infinite number of vertices, because a circle is like an infinite-sided polygon. Let me stop there for a second. I might be pushing my luck with this. If I made 1,000-sided figure, each side would be stupid small, yes? So I wouldn't have to get very far away and it would look just like it would just be a circle, yeah? So if I make it infinite-sided, so what shape do I get? And I don't have to do everything, I just do 2 representative ones on the edge. But everything connects to it, right? So I got this, I got this, I got this, so forth, yes? What shape is that? A cone. But outside of this book, that is the simplest pyramid. Why is it a pyramid? Because we constructed it the same way we constructed the others. The definition of a pyramid is you make a base shape and you connect all the vertices to the one apex point. That's what we just did, yes? And just to get a little ahead of myself, because I can't stop myself, and you're all like, just do what you're gonna do, dude. Does anyone know the formula for the volume of this? What's the shape here? Circle. It's got a radius, yes? What's the area of that circle? So the radius is r, yes? What's the area of a circle? All right, let's do this. Take a circle. Cut it down the middle, yes? One time I'm going to do this, I need to do this with construction paper or something. And then if you take the center and you cut out to the sides, yes? So I'm making little pizza slices, you with me? How long is each one of these? By definition. That's the center. How long is each one of these? Half the diameter, sure, which is also called the radius. So each one of these is r, yes? You with me? If I slice down the center, so I chop the top off, I behead this circle, chop, and then I slice out but not through. I slice out but not through. Are you with me? Can you remember? I think I did this last semester with my guys, but I'll do it again. Pick that up and open it up. Can you imagine that? I want to pick this up and open it up. It'll look like this. Yes? Do the same thing with the bottom. Pick it up, open it up, and shove it in here. Yes? Pretend like that goes all the way down. What's the formula for the circumference? How far around is this? Not the number of degrees. How far around if I walked it? 2 pi r. Yes. How far is it from here to here then? Pi r. You guys, does that make sense? Because it's halfway, yes? Isn't this the same as this, yes? Because I just picked this up and open it up, yes? So these 2 points are here and here. This is pi r, yes? And how long is this? R. And what's the area of that rectangle? Pi r squared. Okay. Has anybody ever seen that before? No. Okay, maybe. So, coming back. What's the area of the base of this? Pi r squared. And let's say it's h tall, yeah. So how many circles are stacked up here? If it's h tall. H of them. Does that make sense? I have h circles. So if I take the area and I multiply it by h, that'll be the volume this thing goes through. So the formula for the volume of this, of any prism, to be honest, is the area of the base times the height. Because I got that many of those shapes. Does that make sense? So this guy's volume is pi r squared. Now, if this was solid, pretend like that for a moment. These are almost, yeah, these are the same height, good. Couldn't I, like, whittle this down and make this out of it? Do you think I would have to whittle off more than is left or less? Let me see if I can answer that question again. Considering this is all the way around, would I have to like chop more of this off than what's left? Yes, I'm just gonna tell you. In fact, what's left is exactly 1/3 of what was there. This is 1/3 the volume of this. That is true for every pyramid. Every pyramid came from a prism. And let me prove it to you. Not prove it, but I'll show you another example. Do you guys agree with me that this is a prism? Repeated shape is either a square on the sides or a rectangle, yes? If I pick a point here, and I connect all the vertices to it, then I just chop out a pyramid. Now, from my drawing ability, that is amazing. I like drawing pyramids because they actually come out okay for me. So I'd have to chop off 2/3 of the block it came out of to leave the pyramid in there. Any pyramid will be 1/3 the volume of what I cut it out from. And that is true for cones. That's why, as a mathematician, I call a cone a pyramid. This book is not going to see it that way. The book has defined a prism and so forth, a pyramid, to have polygon faces. Yes? Okay. Which is okay. We'll be fine. Up, up, up. So going back to stuff about pyramids, if they have a regular polygon base, and somebody remind me, we already said this earlier, but what's a regular polygon again? Yeah, all sides and all angles are congruent, yes. If I use a regular polygon base and the lateral faces, and by the way, everyone I've done, what shape are the faces of this pyramid? Doesn't it make sense that it always has to be a triangle if I have a polygon base because they have to go to one point? So if I look at a face, it's one vertex, another vertex going to a point. Of course it's a triangle, yes? So if I have something where I'm using a regular polygon base and the lateral faces are isosceles triangles, we call that a right regular pyramid. So if I would have made this base square, I would have made a right regular pyramid. kind of in keeping with what we said earlier about prisms. If I don't use isosceles triangles, and some other triangle instead, it's called an oblique regular pyramid. There's a classification of polyhedrons. We call them regular polyhedrons. So a regular polyhedron. Can anyone guess what's got to be true about this? So polyhedron in general is any enclosed space where every face is a polygon, right? What do you think a regular polyhedron is? So polyhedron, again, what's a polyhedron composed of? Me joining together what? A bunch of
Seats.
sure seats, but what do we call the shapes? They gotta be some kind of what? And we're not currently taking a quiz, so you can look at your notes. What do I construct a polyhedron out of? Polygons. So a prism, according to the book, is a type of polyhedron where the two opposing faces are the same shape, yes? So it's a more specific polyhedron. So any polyhedron, I make it out of polygons. So what do you think a regular polyhedron is?
The same polygons?
Yes, but not just the same polygons, but the polygons themselves have to be regular. Meaning, if I want to create a polyhedron out of triangles, what triangle do I have to use? If I want to make a regular polyhedron, I have to use an equilateral triangle, yes? Because that is the trigon that is regular. Okay. So a regular polyhedron is one where all faces are identical, regular polygons. And so real quick. Okay. To be a regular polygon, I needed all my sides to be congruent and
Your angles.
my angles. So to be a regular polyhedron, I need all my faces that are like 3D sides to be congruent and regular polygons. But I also need the internal angles. And what do we call those? Do you remember? No, the internal angles. The angles between the faces. Start with a D. And all dihedral angles congruent. Now, with that in mind, all right, I understand. I can see in your faces. You're like, dear God, today has been so exciting. I'm not sure what to do with myself. I get that, so I appreciate everybody remaining seated. Stay with me now. So some days we're going to have this. We're going to have just me sitting up here going, the dihedral angles. All right. Tomorrow, everybody's going to, not tomorrow, but next time you're going to bring your kits. We're going to be constructing some shit. We're going to see how things kind of go together. I'm going to put you in groups so we make sure everybody has enough pieces. Yes? Would you all agree that there are a lot of requirements to be a regular polyhedron? You have to use the same regular polygon to make all of your faces, and the internal angles between them must be the same. Do you agree? That's a lot of restrictions, yes? So it's really trippy. And to be really broadly honest, there's more than this if you allow for these trippy freaking star-shaped shit, but we're not going to go there. there are 5 solids that actually meet those requirements. And they're called does anybody ever heard of Play-Doh? Not Play-Doh. Not the stuff you ate when you were little.
Tastes like yellow.
No? Yes? But Plato, right? Plato? Socrates, Socrates, Plato, Aristotle, all those weird ass people that had too much time on their hands. I've lost my writing utensil. There it is. There's one of them. Oh, here are the Platonic solids. Here they are. So if I use 4, let me only demonstrate the last one. 4. 1, 2, 3. 4 is the backside. Equilateral triangles, and this is not really well, what do you call it? Proportioned. I think I blew the picture up so it looks more like an isosceles triangle. I get what's called a tetrahedron. By the way, you're not going to have to memorize all of these names. The cube is the most basic one. That's the one I would think of first. Even though a tetrahedron is made of a lower number of side figure, cube is the automatic one where every face is a regular polygon, square. The internal angles are all 90 degrees, yes? The octahedron is neat, right? You can see why we call it an octahedron, because how many triangles go into making that? 8. And then down here, this is definitely harder to see. We have the icosahedron or icosahedron. It kind of depends. And the hedron again means seats, and icosa is a part of the word from Greek that means 20. So this is a 20-sided, it's made up of 20 equilateral triangles. And then you have the dodecahedron. Yes. Not quite. I understand why you say 10. I thought for a minute you said 12, because 12 is what it is. This is 12. Deca would be 10. So dodecahedron is 12 faces. This one is made up of regular pentagons, yes? You guys see that? You could have a non-regular dodecahedron made up of other things. Dodeca means 12-sided, yes? But a regular, if I make a dodecahedron out of pentagons, I get a Platonic solid. Okay, so these are the 5 big shapes that Plato kind of proved were the only ones. Later we discovered there's more, but they get really, really trippy. So we're not gonna, I just wanted to let you know they kind of exist. They're these spiky shapes, which is neat. For us, we have 5. Okay. Well, come on. Oh, beautiful. So here's the thing about these guys. Let me see. Can you guys, let's see, help me out. How many faces did this have again? 8. How many vertices does this have? Let's see, 1, 2, 3, 4, 5, 6, right? 8 faces, 6 vertices. How many edges does this have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes? 12 edges. What is F plus V minus E? Oh boy. 2. It's always 2 for the Platonic solids. And it's also true for any, so this is always true for any convex polyhedron. This little formula, and this is a formula, I would give to you. I'm not going to make you memorize this formula. It's just a neat little side note about how these things are constructed. blah, 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 blah. So if you try to do exactly what I just did with all these other guys, it would work perfectly in this equation. One reason people don't accept the other possibilities for this is two of them don't meet this equation. The ones I was talking about, the other ones that are like spiky, made out of stars. Then you get these really funky, you're like, everything's been funky so far, Jeff. These funky shapes, and I thought I brought examples, but maybe not. Shoot. I think the book has some. You get shapes, and I think somebody made one of these when you guys were playing around with this stuff. Yeah, here we go. Where's a really good example? Yeah, this is perfect. I think somebody made this, if I remember correctly. So this is called a truncated cube, because you'll notice where it wants to be an edge, where it wants to be like a vertex, there's a little triangle there. It's like somebody took a cube and chopped every vertex off and made a little, looks to be an equilateral triangle. You guys see that? So these are called semi-regular polyhedra, because every shape that every polygon I'm using is a regular polygon, but it's not the same regular polygon. So this one's got, let me see if I can tell. Well, it looks like 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, looks like an octagon on the side and a equilateral triangle on the vertices. Yes. So they are regular polygons, but they're not the same one. So a semi-regular polyhedron has all regular polygons, but not the same ones. Now, I'm going to shut the hell up for a bit. I'm going to let you watch little people work with some of this stuff, okay? And I'm going to stop recording so I don't get copyright strike. Because I think we're all feeling a little beat up. What was the last thing? Oh. Let me do this. Let me give you guys this, and I think we'll do a little bit of this, and then we'll finish it next time. Yeah, I think I want to. Well, no. I'll tell you what. I'm not going to give this to you yet. There is something next time. I'm going to have us, if we all bring our kits, we're actually going to have like things we can lay out and then try to fold them up to make certain three-dimensional figures. Yes? So that's going to be nice. So some of you guys kind of happened upon some three-dimensional figures you created, but it'd be nice to know kind of like how to lay it out so you can make it a specific kind of shape. But I think the last thing I want to talk about are two things. A little bit more about cones. Let me give that. I'll give that out next time, I think. Yeah. So, to be honest, I can kind of generalize the idea of a cone a little bit. If I take any simple closed curve and connect all the pieces, all the sides of it to an apex point, yes? That's the, and of course that point I picked can't be in the plane of the curve because then it wouldn't be 3D. That is a cone. What we consider to be a cone is the simple closed curve is a circle, and then I make an apex point there. That looks more elliptical, but it's okay. We're looking at it from the edge. If I make a cone and the apex point is off to the side, that is oblique. If I make a cone and the apex point is directly above, that is a right circular cone. This would be oblique circular cone. Why is that? Because if I drop the height down, what angle does that make with the base? It's gotta be right, because it's all symmetric when I do the blush. Okay. And then the very, very last thing, a sphere. So if I try to draw a sphere, very often we can do it, we can sort of approximate it by doing this here. Some of you guys might put the little thing like that on it, yes? I don't know if you guys ever tried to draw spheres. This circle here is a cross section right through the center of it, and this I would call a great circle. So we often talk about great circles on the surface of the earth, yes? So if I try to get from one point to another point, the shortest distance between those 2 points on the surface is a circle, is a part of a circle. So if I look at any other location that's not the diameter and I make a circular cross section, this is kind of silly, we call this a small circle. The radius of the great circle is unremarkably the same as the radius of the sphere itself. Yes? Okay. Not too surprising. I like it. We're not going to focus too much on spheres yet. I mean, in our future, we're going to talk about the volume formulas more in depth. I kind of gave us one volume formula earlier. But they're going to be based on the general shape of something. So every pyramid has the exact same formula for its volume, for example. Okay, I'm feeling like potentially all of us could use an early ending. So let's do that. Look at that. It's the happiest I've seen somebody all day. Let's do that. Next time, please bring your kits. I'm going to try to, I keep meaning to go by the library and pick up whatever kits are still there, so I can kind of give out anything anybody's missing. Yes? Try to make as many complete kits as I can. Yes?
Would you be able to put a reminder about the kids?
Yes. Let's see. I have to remind myself to do that somehow, and I can do that on my phone.